Hi, this video is a part of Machine Learning from Scratch playlist. In this playlist, I explain different machine learning algorithms implemented from scratch using Python. You can download the relevant Python files from the link given in the description of each video. Note that I do not code along, rather I make use of pen for explaining the tricky parts of code so that you people can read the notebooks and Python files and understand them yourself, and of course re-implement them yourself. I'm expecting my audience to be well versed with machine learning general understanding, and they just need little hints for implementation of algorithms from scratch. In this video, I'll explain ADA boosting algorithm and its implementation. Let's jump to the whiteboard and then notebook to explain the idea and code it in Python. So in ADA boosting, the basic idea is to combine simple models to create complex model. This is the main idea. So how do we do it? Suppose this is a classification problem. If we have to do complex modeling or create some kind of a complex machine learning model, so what that complex model will do is that it will find out this classification boundary, this complex classification boundary, and this might solve the problem and it might not. It might be in overfitting to this training data, and there could be issues in that, and it is really difficult to find out such boundary learning these kind of algorithms and models. Now the main idea of ADA boosting is to create simple models. Suppose a logistic regression is a simple linear model. What we do is we create a simple line. This line, what this line will do is that it will separate blue from the orange. Suppose anything below this line is called orange by the classifier, and anything above this line is called blue by the classifier. So it means all of these points are classified correctly. And if we look at it in a way, all of these points are classified incorrectly, and in the same manner all of these points are classified correctly, and all of the orange points in this area are classified incorrectly. However, some data points are classified correctly while some other data points are not classified correctly. So in the first simple model, what we will do is we will look at the total efficiency of that simpler model. So this is like finding the efficiency of first simpler model. In this case, we will look at the total correctly classified and total incorrectly classified examples, and we will find out the weight or the efficiency or the effectiveness of the first simpler model. Then we will store that weight of that first model. Then what we will do is we will add weights for each of these data points, and the weight will be actually representing the importance of the data point for the second simple linear model. So all of the data points which were classified correctly will be given lesser weight because we don't want to learn them because they have already been learned by the first model. Instead, what we want is all of the models which were classified incorrectly, we want to give all of those data points higher weights. So in a way, we will give weight for all of these data points depending on whether they have been classified correctly or not correctly. Once we give weights, then the second model will learn this setting and this classification problem, but this time this second model will learn the weighted data points. By weighted data point, what do I mean? By that I mean that this time this second model, instead of this horizontal line, the second model will find out this vertical line. Why? Because second model is more concerned about all of the points which were incorrectly classified by the first model. So all of these points and all of these points, of course. So both of these set of points were incorrectly classified in the first setting or in the first simple model. So we gave higher weights to those not learned well, and lower weights for those samples which were learned already well. So in this way, the second model will learn those second set of weights. Then what we will do is we will repeat this task. Then we will find out the efficiency for the second model. This efficiency will be also calculated for the second model, and we will also adjust weight for each of the data points given the predictions and given the performance of each of the data point. Once completed, once a lot of models are created, suppose we created 10 different models, we created ensemble of 10 different models. This is what we call ensemble. ADA boosting is basically ensembling method. So if we create ensemble of 10 different models, so we have weight for each of the model, that how much effective that model is. And after finding out that weight, moving from one model to the second to the third, we also adjust weights for each of the data points. So this is the basic idea. I hope so it is clear. Then at the prediction time, we just predict using all of the 10 models, but the prediction of each of the model is actually weighted by its respective weights. Suppose the first model performed, the weight for the first model is 0.7, so we will multiply this 0.7 value with each of its prediction value for each of the data point. The same will go on for all of the other models. I hope so this makes sense now. This is the basic general setting. We create different models and we weight each data point. So the only thing that will change in our whole paradigm, in our whole what you call the metrics, and in our whole setting, is that addition of this weight matrix. Initially we will be giving 1 to all of the data points. We want to equally weigh them because we don't have any information. So in the first in the application of first simple model, we will weight them all 1. Once we classify or we apply this first model, after first model we will adjust these weights accordingly, and then we will apply the second model using these weights, and then the third and fourth and fifth. It will be, the whole process is finding out the weight for each of the model, that how much effective that model is, and finding out the weight for each of the data point, that in the next model which data point should be given more weight depending on its previous performance. This is as simple as it is. I mean, it is really simple. The idea is really simple. Now let's look at this kind of iteration. In ADA boosting, we have this simple iteration where we find out the weighted error. In the first setting, for the first classifier, the weighted error is equal to the simple error because weights are equal to 1, so it won't make any difference. But for the second classifier, the weighted error will really make a difference because all these samples which are having lower weights will be contributing less to the error, but all these samples which are having higher error will be contributing more to the error. So the model will adjust itself according to those higher weighted data points, or in other words, those data points which were not classified or learned correctly in the previous by the previous models. So after finding the weighted error, we compute the simple classifier coefficient or contribution. And how would we do that? We will find out with this formula, 1 divided by 2 into log into 1 minus weighted error divided by weighted error. You can find this formula in internet, and there are a lot of articles about it. And then what we do is we adjust weights for each of that data point. So if it is correctly classified, then we decrease the weight, and if it is not correctly classified, then we increase the weight. This is again also very simple formula, and you can find out the details for that also. Then finally we also normalize all the data point weights. Okay, so we can use any classifier, but we'll be using decision trees. I'll come to that, but before that, as I've already explained, that at prediction time it is just a linear combination of all the simple classifier. So the prediction given by the first classifier multiplied by its coefficient or its weight or its effectiveness, and then the prediction for the second by the second classifier and its weight, and they all are added together. So this is kind of a linear combination. And now, okay, in the notebook I'm going to explain this ADA. I'll be implementing that ADA boosting tree using decision trees. Why? Because I've already implemented decision trees, and that video is placed in my machine learning playlist, but I will not be explaining that implementation again from scratch. Rather, I've already explained all of the scratch implementation for the decision tree. I'll be showing the code again. I might go a bit about it, but I'll not explain basically the decision tree implementation. I'll just explain the changes that I have done because of this ADA boosting part, and the changes is basically only in the error calculation, where we find out the weighted error. And other than that, ADA boosting will contain another, for ADA boosting I'll be adding only another function which will be doing this logic, this for loop that I have explained. So this for loop will be inside a function that I'll be explaining. So that one function and this weighted error calculation will be the additional thing. Otherwise, the whole decision tree implementation will be same as I have already explained. So you might watch that if you are interested in that. But if you're not interested in that, then you can also use the scikit-learn's implementation. You can also use the logistic regression or whatever you want to use as a classifier or a regressor. Now, okay, one more detail, that decision tree we will be not the simpler classifier that we will be applying is not a complete decision tree. Instead, we will be using a single level decision tree. So this is what we call a simple classifier. If we allow the growth to go down and down, so then that is not a simpler classifier. Instead, it is even the very complex classifier where we overfit to the data. So a single level decision tree is actually what we call a decision tree stump. So this is the terminology that we will be using. So we will be applying decision tree stump as a simple classifier. If this terminology is clear and this this for loop is clear and general understanding of ADA boosting and these adjustment of weights for each of the data point is clear, then let's jump to the notebook. Okay, so this notebook will be very much familiar to you if you have watched the binary decision tree implementation from scratch video. So we import the Theory Create, which is a combination of scikit-learn and pandas, and then we load the lending club dataset where we are predicting loans, if the loans are safe or not. Then we select 4 categorical features that we will be using because we are dealing with binary decision trees. So then in the future, so that's why we extracted these categorical features, and we will convert these categorical features into zeros and ones. And then what we'll do is we subsample the dataset because we want to work with the balanced data set, so we undersample the larger class, and the safe class is, I think the safe loans is actually the larger class, I think so. Okay, so we transform the categorical feature into the binary feature using Python and Theory Create internal functions. You can do it in any way if you want it, but that's not the important part. The only one function, the two functions are very important in this whole setting, which is basically related to ADA boost. All other details are related to either dataset or binary decision trees. So I'll just directly go to those areas. I'll just bypass all of these details. So these are like kind of features. Then we split these train test, and then we find out this weighted decision trees. So we had already explained the decision trees, but in weighted decision trees we find out the weighted error, and weighted error is including this alpha terms. This is the only new term that we are including, and we are dividing also by this alpha terms so that to normalize it. And how do we do it? So in this finding the total weight of mistakes, we are multiplying with this alpha terms. So we will be writing the function for this weighted mistake formula. So we have already looked at this function of intermediate node weighted mistakes, so where we are internally finding out the errors for every node of a decision tree. And how do we do it? I have already explained, but one thing that we are actually including into it is basically the weights, the data weights that we have just included. So for all of the positive examples, so these are all weights for all of the positive examples. So where we are extracting, given the label, if the label is +1, so we are extracting the weights for all of the positive examples, and these are all of the weights for the negative examples. And then we are just the remaining logic is exactly same as I have already explained in the previous setting of binary decision trees. If you are not working with binary decision trees, then again in whatever classification algorithm or any other algorithm that you are using, you have to incorporate this simple logic of finding out not just simple error but this weighted error. So in decision tree, this logic looks like that. But if you don't want to work with decision trees, it's okay. We can work with any other algorithm, but you have to incorporate, the important part is this weighted part. So once you do it, you're good to go. So this is the single part that we have added. All other functions are exactly same for decision tree implementation from scratch. You don't even need to look at it. So this is finding the best splitting feature. All of the things are here same except for using this intermediate node weighted mistake, and not just intermediate node mistakes. So we are just calculating the weighted mistakes. Other than that, we create leaf node. We have already explained that, which is again same. We create this weighted decision tree model. This is again same except for this using these data weights where we are extracting the weights for each of the feature. So like if we have some kind of a splitting feature and we are extracting the data, so we are not only extracting that data, but we are also concerned with extracting the relevant data weights. So for left split, we are extracting these left split data weights, and for right split we are extracting the right split data weights. Why we do it? Because we need to input these weights as in the function of finding a weighted error, as I already explained. Then counting the nodes is again same. Then this classification function will be same. Okay, after applying this class, okay, after that now is a time to basically, this is the important function, this is the actual function which is a crux of this video. So this is the main thing that we have to apply in kind of implementing ADA boost algorithm, where we are giving data as an input, features and targets, and number of tree stumps. Number of tree stumps means number of simple classifiers. As we are using decision stump as a single classifier, that's why we are calling that number of tree stumps. If you want to use any other classifier, then here the number of classifiers will go in this part of the argument, in this part of the function argument. Okay, so what we do is we start with the unweighted data, where we are initializing all the data weights with 1. then we keep track of all the weights. Decision trees are simple models and the target values. So these weights will be for each of the decision tree, a stump, or any other linear model, or any other simple model, and the weight will be its relevant weight or coefficient, as I already explained. So for each of this tree stump, what we will do is we will find out, we will create that weighted decision tree. If you are dealing with logistic regression, then you will find out that weighted logistic regression where weight will be equal to 1 in the first case, and then you will what you'll do is you will do prediction. Because we have implemented it from scratch, so we are using our own function for prediction. But if you're using scikit-learn's implementation, so you will simply predict using scikit-learn's function. Once you have predicted, then you will find out whether the data point was correct or not, data point was correctly classified or not. So based on correctly classified or not, what we will do is we'll find the weight of the model coefficient looking at the whole weighted error. So this is like the efficiency of this is like computing the efficiency of whole of the simple model or the decision tree stump. Once we have done that, then we will adjust weights based on this formula, exponential minus weight if it is correct. If it is not correct, then exponential weight. So this is adjustments. Once adjustments are done, then we normalize the data weights. These alpha contains the data weights. Okay, so once we do it for all of the iteration, and in the process we store the weights and coefficient of the simple models, and we store also the simple models. This is a simple setting, and this is what we call ADA boosting. Once you understand this part, then there is nothing remaining in this whole notebook. So then we are just implementing it. We are just printing the stumps that we have just learned in the ADA boosting function. So once we have learned it, then we look at the weights, stump weights. So these are the stump weights by stump I mean the simple model. These are the weights for each of the simple model, and this is actually a prediction part of ADA boosting. So this is where we predict, but each of the prediction is multiplied with its weight or coefficient. So this is how it works. Now the whole idea is really same. This is a performance plot. If you look at it, like how it goes as the number of iteration increases, there is nothing remaining in it. The most important part is, of course, this prediction, which is not that much difficult. The most important part is basically this single function, where we are applying simple weighted model, where we are calculating the weighted errors. We find out the effect or efficiency or weight of each of the single model that we are using, and then we adjust the weights for each of the data point, and then we repeat. If you understand this part, then I think so you have understood the ADA boosting.